Hello everyone, my name is Luis Pena and for today I will be covering assembly math operations. I will first begin by giving some general knowledge of assembly operations and through registers and how they are connected and how you can piece everything together to gain a better understanding of how math operations in assembly works. I will first begin with this slide. So here I have registers in the form of a computer. We have EAX, AX, AH, and AL. I put AH and AL because they have similar size. So here to the right we have the size. We have EAX, which are 32 bits, AX, which are 16 bits, and AH and HL, which are 8 bits. So here I drew a picture in Paint where I have register sizes and their connections to each other. We have EAX, which is the grand picture, we have AX, which is the smaller 16 bytes, and we have AH and AL, which are 8 bytes. Moving on, I will now show you the max capacity for the different registers and their sizes. EAX, which are 32 bytes, have a max value of this. AX for 16 bits have a max value of 32,768, and AH and AL are 8 bits, which have a max value of 128. Moving forward, I will first begin with my first math operation, addition. Some general guidelines for all the operators being used. The rules of PEMDAS will be followed such that when doing any sort of math, parentheses, exponents, multiplication, division, addition, and subtraction will be conducted in that order. First, we have addition, 8 bits. I drew this picture where it covers code on the left hand side and comments on the right. We have this command block, move BL 50, this passing 50 to our register BL, move AL 60, this passing 60 to our register AL. The first one was BL. Then we have our addition operation, add AL and BL. Note here we have two cases, both registers are involved, and after that we just zero it out. This will become important for future cases. And I just put some notes here, the result is placed in AL. So 50, 60, addition is 110, and I just zeroed out BL. Moving forward, we have addition through 16 bits. We have AX, which is a 16-bit register. We have BX, which is a 16 also bit register. And we have values of 5,000 and 25,000. Here we have the addition operation, and the results are placed in AX, which you can see the change from 5,000 plus 25,000 gives you 30,000. Moving forward, we have addition through 32 bits. We have our registers EAX and EBX that have values of 350,000 and 500,000. Here we have the bit sizes for comments so you can gain a better understanding. We have our addition operation. Again, we have two registers involved, and the result is placed in EAX. And our grand total is 850,000. Moving forward, we have the next operation, which is multiplication. I added this note that the multiplication operation differs from the addition operation because the multiplication operation handles one register, while the add operation handles two registers in its command block. The operation looks like mul BL, which was different from add, AL, and BL. An example of an 8-bit would be this code, a AL, which is an 8-bit register passing in the value 128, a BL, which is an 8-bit register passing in a value of 2. We have our multiplication operation, mul BL, and the results are in the AX, a 16-bit register. Here we go, 128 times 2 gives you 256. Our next case is multiplication through 16 bits. We have the register AX, a 16-bit, and the register BX, a 16-bit. we will be passing in 32,768 and 5. We have our multiplication operation, and the results are different this time. The results are in half of dx and half of ax. dx and ax are 16-bit registers, so the product is in a 32-bit. The multiplication of these two values is 163,840. Therefore, the answer is distributed in half of dx and half of ax. Here we have multiplication of 32 bits. We have a 32-bit EDX and a 32-bit register EAX. We have values of 350,000 and 7,000 for these two registers. We have a multiplication operation right here. The results are different this time too, because it will be placed half in EDX, a 32-bit register, and half in EAX, a 32-bit register. These two are both 32-bit registers, so the product is in 64 bits. The multiplication of these two values is 2.45 times 10 to the 9th power. The result is distributed half in EDX and half in EAX. Moving forward. Lastly, we have our last operation, which is division. Division operation, like the multiplication operation, handles one register in its division command block, but with division comes a possible remainder. Remainders are stored in specific registers, and they must be zeroed out after the use. We have 8 bits. Here we have code to the left, comments to the right. We have an 8-bit registers, AL, BL. We have values of 9 and values of 2. We have our division operation right here, similar to that of the multiplication command, and the remainders are placed in AH. Remember to always zero it out after a certain procedure is done, and the result is placed in AL. So 9 divided by 2 is right here 4 with the remainder of 1 for 8 bits. We have division with 16 bits. Here we have a 16-bit register AX and a 16-bit register BX. We have values of 259, values of 2. 259 divided by 2 gives you this value of 129, with the remainder being 1. So here we have to the left, results are in AX and the remainder is in DX. Finally, division with 32 bits. We have the division operator, 32-bit EAX, and the 32-bit register EBX. For the values, we have 500, 1001, and 2 for EBX. We have our division operation. The result is placed in EAX, as you can see right here, and the remainder is placed in EDX. So 500,001 divided by 2 gives you 250,000 with a remainder of 1. This was my presentation on assembly math operations. I hope you enjoyed and you gain a good understanding of the topic. Thank you and have a good day.